In this video we're going to go through some examples using rounding. Now we won't go through every possibility, but we will look at 8 different examples here, and it'll give us a good indication and a feel for the rounding. So if you open up the Logisim file in the resources section and you click on the top level, it'll take you here, and you can also open up the spreadsheet. So what we'll do is we'll get into the spreadsheet first of all, and whenever we click on the add subtract, it's going to bring up our usual box, so we can close that for the moment. Now what we're interested in with the rounding is what happens whenever this Y bit here gets shifted to the right and generates the values. This Y value here shifts to the right and it generates these values here. So we're going to have a guard bit and we're going to have all of the rest of the bits, which we can just call the sticky bits. So I've already worked out a few examples here, so let's just start working through. So the first one we're going to look at is just a addition. So we're going to have 560.1 and we can add on 7.1. So you can see here that the correct answer here is that 440D-CCC. Now I've already put these values into the Logisim, and you can see here I've put the same values into Logisim and I've get the 440D-CCC. So the Logisim does exactly as we expect it to do. Now this is an example of, say for example, you have a number, the final answer is say 5.3 and you're rounding it to the nearest integer. So in which case you would be rounding that one down because it's less than halfway. And we can see that whenever we look at the actual values. So when we go to the final answer here, you can in row 23, you can see here that we're going to have the least significant bit as a value of 0. And I've got the guard bit here. Now the guard bit here is the value of 0, and I've just copied it here. And the round bit, we said the round bit was going to be generated by ORing all of the remaining bits. So if any one of these bits goes high, then the round bit will be high. So you can see here the very first one is going high, so the round bit is high as well. So for these we're going to have a 0, 0, 1. So it means that we've got an even number because it's the last number is a 0. The guard bit is a 0, so that means that it's going to be less than the halfway, because the first number here would represent 1 upon 2, and this number, the number after, would be 1 upon 4, 1 upon 8, 1 upon 16. So this is 1 upon 2 and it's 0 in it, so it means that it's less than that value. There's no value of a half, so it's less than a half. So it doesn't matter what happens with the round bit, this bit's less than a half, therefore we just round it and we just leave it exactly as it is. Okay, so it just means that in effect we just cut these off and we just leave the least significant bit as a 0, so there's no addition of that 1 here. So that works exactly as we would expect it to work. Now we'll put in another example here and we'll do the, if I add in tools, add subtract, and we can put in 560.1 and we could put in say 7.13. Now this is an example of, say for example, 5.7. So, and we'd be rounding it to the nearest integer. So the nearest integer would be rounding up to 6. Now we can see that here if we head down into the spreadsheet again. Now in the spreadsheet you can see that the final answer here, the least significant bit is a 1, so it's an odd number. And you can see that the guard bit is a 1, so we've got the guard bit from here, we just copied it down. And we can see that the rounding bit's going to be a 1 as well, because we've got 1 for at least one of these sticky bits. So that means that we've got a 1, 1, 1 here. So the least significant bit is a 1, the guard bit is a 1, so we've got a value of at least a half. And the round bit here tells us that we've got another number here that's going to take us above the value of a half. So that means that we're going to have to round this up. Now in order to round it up, we're going to have to add a value of 1. So you can see between this line here, which is the answer, and the row 24 is the rounded answer, we've added a value of 1. So when we add value 1 onto this, you get 1 plus 1 is a 0 and we carry 1. 1 plus 1 is a 0, carry 1. 1 plus 1 is a 0, carry 1. And then we just have that value of 1 there. So you can see that this one here has been rounded up as we expected it to be. Now the other two examples we're going to look at are the more interesting ones, which are the halfway point. So if I was to head in and we put in another couple of values. Now again, these values were just kind of randomly found by myself. I just put some numbers into, I found what I was looking for. So 56.6777, and let's say we add on the value of 7.15555. Okay, so I can close this one down. Now in this instance here, you can see here that the least significant bit is a 1. We've got the guard bit as a 1, so I've copied this here for the guard bit down into here, so that's a value of 1. And you can see after that we have all zeros, so if I was to head all the way along here, all the sticky bits would be all zeros. So that would mean that the round bit here would be a value of 0. So we're exactly halfway here. So we've got a value of a half, and then we've got all zeros afterwards. So the question then is, how do we round it? Well, we use the nearest even rounding. So you can see that the least significant bit here is an odd bit. So what we're going to have to do is we're going to have to add 1 to it in order to do the rounding up. So if I add 1 to this here, then we're going to have the 1 plus 1 is a 0. So that means that we're definitely going to have an even answer because the last bit here is a 0. So 1 plus 1 is a 0 and carry 1, and we have 1 plus 1 is a 0, carry 1, 1 plus 1 is a 0, carry 1, all the way along till you get to this point here. So you can see here that we have in fact rounded this to the nearest even by adding 1, and you can see that we've definitely got an even number because the least significant bit is a 0. Now the final one here out of this lot is going to be 56.67, and we're going to add on 7.15555. So if we can close that and we'll have a look at the values again. So you can see here the least significant bit here of the answer is a 0. The guard bit is a 1, and you can see here that the round bit is a value of 0. So in that case you can see that we are exactly halfway. So if we're exactly halfway, what we do is we look at the least significant bit now and we round towards that least significant bit. So in this case here we're just rounding down. So it means we don't add 1 onto it, it just remains exactly as it is. So this here just follows the same little truth table that we've seen whenever we worked out our nearest even rounding. So that's the 4 possibilities that we were really interested in, and that covers it for the first example, which is an addition without any ripple. Now rather than going through the last 4, we'll just do the last 2. So we're interested in what happens when we have an addition and then we ripple. That is, we add 2 numbers and the summation of the 2 numbers goes into the next exponent range up. So if it goes up into the next exponent range, we're adding 1 on to the exponent, and in order to normalise it, we're going to have to divide the mantissa by 2. That is, we're going to have to shift the mantissa to the right. Now when we shift the mantissa to the right, as we said before, what happens is the least significant bit of the mantissa then gets shifted into the guard bit, and then the guard bit becomes part of the first sticky bits. So let's put the numbers in here. So we'll have 15.211, and I'll do it so that we've got a tie position, and we'll see what happens in this tie position. So that's the final answer here, and we'll have a look on the spreadsheet. Now we have to jump about a bit in the spreadsheet, so we'll just take our time. So we're going to have the y value here, and we said that the exponent difference is a value of 1, so that's exponent difference ex minus ey. So we're going to have to shift this to the right. So whenever we shift the mantissa to the right, this entire row here gets shifted 1 to the right, and then we have a 0 in place of this. So instead of 1 1 1, we end up with 0 1 1 1. And what happens is the very last digit here, which is the 0, gets shifted off into the guard bit. And you can see here, that's this 0 here shifted into this guard bit. So the guard bit is a value of 0, and then the sticky bits here are all zeros. So because we're having to normalise this result, we can see that the least significant bit of the answer, which is the 1 here, is going to be shifted to the right by 1. So this value 1 gets shifted into the guard bit position here. And the value that was in the guard bit position, which is a 0, gets shifted into the first sticky bit. And the second least significant bit here gets slotted into the least significant bit, which is a value of 1. So you can see everything just gets shifted right by a value of 1. So it means that the least significant bit is this bit here, which is the 1. And then the guard bit becomes this bit here, which is the 1. And then the round bit, well, is still all of the sticky bits here, which have been ordered together. And there's none of them have a value of 1, so that's a value of 0. So in this instance here, we're exactly halfway. We've got an odd number. The guard bit is a value of 1, and the round bit's a value of 0. So if we were exactly halfway, what we said is that we have to look to the least significant bit, and if the least significant bit is an odd number, we have to make it an even number, that is round to nearest even, so we have to add a value of 1. So that's what we've done here. We've added a value of 1 onto this, and we'll have 1 plus 1 is 0, carry 1, and we end up with this final answer here at the bottom. So there's quite a lot involved in following the ones and zeros round about in that example, but what we'll do is we'll go through one more example which will give us it will give us the tie. So we'll go ahead and we'll do this final one here, which will be 12.55, and we'll add on 4.333. We can close that down, and you can see here that we have our difference in the exponents as a value of 1. And you can see that whenever we've added both of them together, we've got a 1 in this box here, which tells us we're going to have to go up into the next exponent range. So whenever we normalise this, we're going to have to add this 1 to the exponent. And when we add that 1 to the exponent, we're going to have to divide the mantissa. That is, the mantissa is going to have to be moved to the right by a factor of 1. So you can see here that if we were to do that, again, what's going to happen is the least significant bit here is going to move into the guard bit position. So this one jumps into that position. The value 0 here, which was the guard bit, becomes the first sticky bit. And then the value, which was the second least significant bit of the answer, will drop into the least significant bit of the answer. So finally what we're going to be left with is a 0 for the least significant bit, and we'll have a 1 for the guard bit and a 0 for the round bit. Now we can see here that it's going to be a halfway point because the guard bit is a 1 and the round bit is a 0, so that's exactly halfway. But in this instance here, we have an even answer already because the final digit is a 0. So it means that we don't have to do anything in this case. We don't add 1, we just leave it as it is, and we get our final answer, which is going to be the least significant bit is a 0. And that really covers the two options for the ties for the ripple. Now we could go through and do the same for subtraction with cancellation and subtraction with no cancellation, but I can leave that with you and you can try figure out a few numbers and you can put them in as tests to see that those work exactly as you would expect them. Now, not very exciting this video, but it does allow us to pick out a few examples and have a look and see that it does actually work. Now, I've put all of these values here into Logisim, and I've checked that Logisim gives us the same answers as the spreadsheet. I didn't want to do it in the video, it would just take too long. So that's everything for a rounding. We can finally put that to bed, and we'll move on to subnormal numbers in the next section. Thank you for listening. I'll get you in the next video. Goodbye.